Today we're going to talk about active galaxies, active galactic nuclei, quasars. So this is, I know it's getting into the more exotic stuff, I think, in astronomy. I want to start with the ending of last class period. The ending of last class period, we were talking about the distance indicators, and Hubble and what was his name? Humana published data about the speeds at which things were moving away from us as a function of distance. So this is the stuff we looked at last class period about how they calibrated the distance, the different things they used to calibrate the distances. And the bottom one, of course, Hubble's law, they couldn't use that. That's what they developed. So here's the graphs, first Hubble's data from 1929 that showed, and I remember I said, kind of an iffy trend, not a strong fit. And then a couple years later, Humason, that's his name, a couple years later, extending the distance and seeing a much better fit. If you want more information about Hubble's law, this website right here gives you some good insight. But let's talk about what this means, because this is actually a very pivotal piece of understanding. What this graph shows is when you have things that are some ways away from the solar system, they're moving away from the solar system. Almost everything is moving away from the solar system. So if everything's moving away from us, what would your logical explanation be? Center of the universe, says Alex. A lot of people have said that. It's a pretty good logical assumption. It's not the one scientists make, and I'll show you why in a second. Generalizing a little from what Alex said, everything's moving away, so the distances between things are expanding. So the universe must be expanding. That's a general statement that everybody agrees on. The universe is expanding. Now, how big is the universe? We'll cover that in cosmology. The simple answer is scientists believe it's infinite. There is no boundary. There's no end. If you were to go forever, we'd never get to the end. But this says that the universe is expanding. Now, that in and of itself is a monumental change in understanding. Up until this discovery, and remember, I think it was Lemaitre had published a few years before in a Belgian journal about the same idea, but it was obscure and really nobody really was aware of it. Hubble may or may not have been. I said, it doesn't matter to me. But up until then, people assumed that the universe was pretty much static. The distance between the sun and Proxima Centauri is going to stay the same forever. That was pretty much the assumption people had. And now all of a sudden we have evidence that says the universe is expanding. Why would this be a monumental shift in worldview? Worldview is probably not the right term anymore. Universe view. Why would it be a monumental shift?
Saying energy is coming in.
So far, it's not necessarily saying energy is coming in. It does eventually. But so far, it's not. You can have an expanding universe. If you have a bomb, and you detonate that bomb, all of the molecules in the air are going to be moving away from the bomb, right? And so everything's expanding, and it's going to continue expanding for a while. Now, it might stop, or it might eventually, everything escapes and just keeps going at constant speed. Or, there's some options there. But if everything's expanding, that indicates that if you went backward in time, what would happen? They would come together. You would have had a point in time where everything was right on top of each other. And so that's what spawns the whole idea of a Big Bang. Just reversing that timeline, because we see everything is expanding, if we reverse it, we should have come to a point where everything was together at one point. And so it's this idea, you look at the data and it's pretty hard to disagree, right? It looks definitely like the farther things are, the faster they're going. Everything is expanding away from us. And so it's hard to argue against that. Now, one of the key things that's taken from this is finding the slope. And if you go to, now, what the heck? Like, I'm going to be able to go to that website. I could have sworn I set it up as a link, but it looks like I didn't. Well, who can remember that? 25179 Hubble constant. With space, right? 25. Oh boy, I can't remember. It's 119? 179? Trusting you. Hey, good job. Okay, this is a nice article that talks about that Hubble constant. Based largely on that, based on the Hubble constant, we can calculate a time scale from when the universe began. And that time scale, there are some assumptions. So the 13.82 billion years for how long ago the universe began actually doesn't come from directly the Hubble constant, but the Hubble constant gets us to that ballpark. There are two different ways of calculating the Hubble constant here. One, it gives you a slope of 73.5 kilometers per second per megaparsec. That is using objects that are reasonably nearby. Reasonably nearby doesn't mean, in our galaxy, clearly. It's galaxies that are, within, let's say, 5 billion light years from us. And then using the Planck telescope, they can measure farther things and they get a different Planck's constant of about 67 kilometers per second per megaparsec. And so this is a really good place to learn about, that fit. Notice luminosity here is shown versus period for the Cepheid variables to help you understand how the Cepheid variables give you a luminosity. If you measure the period, you know the luminosity. Once you know the luminosity, you measure the brightness from Earth and you can calculate the distance. And, it goes through the different things of how this is done. Hey, look, NASA's James Webb Space Telescope. I've got attention span of a 2-year-old. I'm sorry. We don't need to go to the James Webb Space Telescope page. We'll just go back to our lecture now. So that slope is really important. And our textbook uses different units. I'm going to put here about, up here, it's about equal to 70 kilometers per second per megaparsec. Our textbook uses kilometers per second per million light years, per mega light year. So it's going to be a slightly different number because it's different units. But what we have here is something that relates the speed at which something's moving away from us with the distance it's moving away. So we can take this relationship and we have the speed is equal to the slope times the distance, right? Because the slope is, slope is equal to h, which is rise over the run. And so you just solve that for the speed by multiplying the distance across. And so we have a relationship that gives us speed as a function of Hubble constant and distance. Or, more useful to us now, if we will go back a couple slides, you'll recall, whoops, no, it was just one slide, that redshifts using Hubble's law is the ultimate distance calculator we use. So from this equation I wrote, what we actually do is we solve it for distance. So if you solve this equation in the top right for distance, just going to change color to set it off, you get distance is equal to the speed something's moving away from us divided by the Hubble constant. So this is how we determine the distance for very, very far objects. You measure how fast they're moving away from us, and then you can calculate the distance using the Hubble constant. So it's a really important parameter. Now, I think I mentioned this in class earlier. Gravitational waves might supply another way to calculate Hubble's constant. And so there is hope that now that they've measured a few gravitational waves, they'll be able to come up with an independent measurement of Hubble's constant that would help them narrow this down to understand better about the expansion of the universe. Now, what's going on with the expansion is a really crazy answer. Because if I say the universe is expanding, there's a pretty simple explanation. Things are moving. So we could think of it like, the universe is a flat TV screen, and the positions of things are moving out on that screen. But that is not the scientific answer. The scientific answer is that the fabric of the space-time continuum is stretching. Now remember when I showed you the video of the simulation for gravity? It talks about the space-time continuum. He's mending a tear in the... Anyway, that's really what scientists believe space is. That space is something you can stretch. So the easiest way to understand this really is to think about that, or think about a balloon. If you have a balloon and you put 2 dots on the balloon, and then you blow up the balloon, what happens to the separation between those dots? It gets bigger, right? But did the dots actually move on the balloon? No, it was the space of the balloon stretched. And so that's what scientists believe is going on with our universe, that the space is stretching. So it's not like things that are farther away are traveling fast in space. It's that the space is stretching, so the distance between them gets larger, even though they're staying fixed. So that's what this illustration is trying to show you. It shows a meter stick with ants on it. And then the meter stick is stretched. Notice the ants aren't stretched. But the space is stretched, and so the ants are farther apart because of the stretching of the space. It's a very interesting concept, isn't it? Yeah.
So why aren't the ants
I don't have a good answer for that, Alon. I should, but I don't. His question was, why aren't the ants also stretched? I know that they're not supposed to be, so that the spaces in our solar system are going to stay the same as the fabric of space stretches, so the distance between us and other objects gets farther apart. Here's an example about the center. Remember Alex's first explanation was that everything is moving away from us. We must be the center. This is the diagram, or one of the variations we use for a diagram, to show why that's not actually the logical conclusion. If you have bread with raisins in it, and you put that bread in the oven with some good yeast and it rises, the space between the raisins is going to get farther apart. Do the raisins grow because of the rising? They don't grow. It's the fabric of the space-time they're in this case, the bread dough that grows, but the raisins stay the same. And no matter which raisin you look at, all raisins got farther away from it as it rose. So you can't take any one of them and say, oh, this is the center because everything's going away from it. Because every single raisin will have the same observation that everything's moving away from it. Because the entire space is stretching. You could do the same thing with my balloon example. You could take a balloon that's just barely blown up, put polka dots all over it, blow it up. Every single dot would say all the other dots have moved farther away from it. Okay, they don't speak. We shouldn't anthropomorphize dots on a balloon. But an observation would show that the space between everything gets bigger, and if you choose any dot, the closer dots will have moved a small distance away, the farther away dots will move the bigger distance. So you would find farther away things have a bigger distance per time. Closer things have a smaller distance per time. Exactly what we observed with Hubble's data. So I think it should be pretty clear how this explanation comes around. It's if the space is stretching, we should have everything getting farther apart, and the farther away things are, the faster they're getting away from us. Okay, that brings us to the end of that chapter, and now we start with the active galactic nuclei. So this here, the picture on the left, is part of the very famous Hubble Ultra Deep Field photograph. What astronomers did is they said, you know, it's not like anyone ever uses this Hubble Space Telescope. Let's do something interesting. Let's dedicate, I think they did like 2 weeks, to looking at this one region of the sky where we see no stars. And if we do a really long exposure, we'll be able to see really faint things. And let's see if we find anything in the region of the sky that has nothing. Did they find anything? Mm-hmm. Most miraculously, they found just a vast cornucopia of things. Now, if you look at this, there's only one thing in there that could possibly be a solo star. There's one thing that could be a star. I don't know if you have enough light and contrast. Can you find one thing that's not like the others?
There's that purple one.
What area?
And there's the red one.
This one?
Either that one or the one above it.
Well, it is this one.
No, okay, yeah.
That one there is different. See how it has this X thing on it? That's the kind of artifact. That's not something that's actually happening. That's an artifact we see with our optics when we have a bright speck of light. And so that could be a star. Everything else in that entire picture are galaxies far, far away. So we have all kinds of galaxies. Now, can you identify any types of galaxies? Like, let's take the one that was named the red one a second ago. What kind of galaxy is this? Okay, that's clearly an elliptical. It has the features of an elliptical. It's red. Remember, ellipticals tended to be red, old stars. You don't have any signs of a disk to it, right? So that's pretty certainly an elliptical. Now, can you find other types of galaxies?
There's a spiral one on the left.
Okay, spiral one on the left. This here?
Yeah.
Yeah, I think it is. It's kind of hard to tell, but I think you're right. I think that's a spiral galaxy. And
below it, you have another one looks like a side.
yeah, this looks like we're looking kind of side on, maybe in a spiral.
There's one on the bottom left. It looks like it's on its side. Oh, more to the left. More to the left. Right there.
There. Yeah, it's kind of hard to tell with this picture, but there is a website, and for crying out loud, Galaxy Zoo, I think is the name of it, where they are crowdsourcing, analyzing all of the different galaxies that have been observed. And so you go there and you sign up for an account, and it shows you a picture and it says, what type of galaxy is this? And so you say, oh, that's a spiral or an elliptical or an irregular. And then if it's a spiral, it asks you about the orientation and, is it an A, a B, or a C? And they're doing crowdsourcing, so anybody can sign up. And each object is sent out to, let's say, 10 people. And what they found is even if you have rank amateurs, people who know nothing, if you take the average result from those 10 people, it's going to be pretty dead on. And so they're using that to analyze them. I used to have my students have a requirement of doing 10 analyses just to get a hang of how the process works. So the picture here on the left is visible light. The one on the right is looking at X-rays. Now with X-rays, you see not all the big stuff, you just see little points of light. And so this picture was done, I think around the 1990s or so. And our understanding of these things, what we're talking about today, has developed very dramatically in the last 20 to 30 years. So the first thing we're going to talk about is quasi-stellar radio sources, or quasars. Astronomers looking at the sky found some things that for all the world looked like stars. But when they were able to look at the spectra of them, the spectra didn't look like a star. What is the star's spectrum supposed to look like? What should it have? Yeah, I know Mira's answering, but I can't hear you. What?
Hydrogen and helium spectra.
Okay, you should have some hydrogen and helium spectra. You should have maybe a small Doppler shift for the rotation, a Doppler shift for it moving away from you, and make some absorption lines, some other things. Is that the same as a galaxy? No, it's not. A galaxy has a very different spectrum. Because a galaxy, you have much greater motion. The difference in things coming toward you and going away is much bigger. So you have much bigger changes in the Doppler shift. You still have a Doppler shift for moving away, but much bigger changes. And you're going to have a much more muddled out absorption spectrum because you're looking at a large range of temperatures and sources. So a galaxy spectrum doesn't look like a star spectrum. So they looked at these things, and of course the one in the center here that has the arrow to it is one of them. And you look at the picture, you can't tell that's something different than a star. But when they looked at the spectrum, they said this isn't the spectrum of the star. And so here's another picture. The two things in the center. It turns out only one of those is a star. One of them is something that looks like a star, but it's not. A quasi-star, a quasar. The one in the center is the one that's the quasar, just for the record. So the big breakthrough came with these two gentlemen here. So notice this picture is from 1987. I believe it's this guy here who was the first one to actually make a spectrum, be able to get the spectrum from one of those quasars. And then, I should point out why the quasars were interesting before I get to that. The quasars were interesting because they looked like stars, but they were giving off a lot of radio waves that were unexpected for a star. So that's why the original definition, the one I had here, quasi-stellar radio sources, the radio sources, because that's what they really picked up on initially, that said these are not like a star, because they're giving off all this radio, much stronger radio signals than we should get from a star. So the person on the right there was the first one to actually get a spectrum from one of these quasars. And the person, on your right is the one to get a spectrum. The one on your left was the one who figured it out. And you might say, shouldn't the one who got the spectrum be the one who figured it out? The answer to that comes in no one expects the Spanish Inquisition. When they looked at these things, they saw spectral lines. But the spectral lines made no sense. You have the spectral absorption lines. Made no sense. And so everyone was like scratching their head, what in the world is this? Are these different elements from what we have here on Earth? What's going on? And finally, the gentleman that's on the left in this picture, Martin Schmidt, said, well, what if this is an object that's really moving away from us fast? People knew about Doppler shifts at this point. They had used Doppler shifts already to determine how fast other stars are moving away from us. They said, what if they're moving way faster than we expect? And so he did the calculations, and boom, he calculated that, the object is quasar 3C from the third Cambridge catalog, 273. It was the 273rd item in that new Cambridge catalog. He determined that it was moving, I think, something like, it has a Doppler shift to something like 5 or something. I don't know. This is actually one of the closest quasars that has been studied, but it's still very distant. So here's your Doppler shift equations. I was going to put a picture with this, and apparently I forgot. The non-relativistic Doppler shift is pretty simple. You have your spectral lines, right? Oh, boy. That looks really good if you're on a black background. Not so much here. You have your spectral absorption lines. And then if something is moving, you're going to have Doppler shifts. If it's moving away from you, which direction are they going to be shifted? To shorter wavelengths or to longer wavelengths? Okay, if it's moving away, longer wavelengths are a red shift. So these are going to be shifted so that they're like here, 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 you know, they're shifted out. And so for each one of those, you have the shift in wavelength there I marked with the aqua, and the wavelength it has in the laboratory I've marked with red. And so Z is what we call the redshift. So Z, the redshift, is equal to, so we should have delta lambda 1 over lambda 1 equals delta lambda 2 over lambda 2 equals delta lambda 3 over lambda 3. So the first thing is you can actually check. You're not just doing one line and saying that's what the redshift is. You check a bunch of lines and see if you have this fixed relationship for the family of lines, like in the Balmer series. And if you say, okay, if this is the first one in the Balmer series, this is the second, this is the third, do they all give me that same redshift? If they do, then you have some confidence. If they don't, then you say, I must have been wrong. Let me reanalyze. So Schmidt did this and found, yep, they had the same redshift, but that redshift was huge. Now, for this top equation, the non-relativistic equation, if you solve that for speed, you have speed is equal to the speed of light times z. So you calculate what that z is, and that z might be, let's say z is 5. That's a really big shift, right? I mean, if you have 400 nanometers and you have z is 5, that means the shift was 5 times 400 is 2,000 nanometers. It's now in the infrared instead of in the visible. That's a pretty big shift, which you can understand why people would ignore that, not think about that kind of shift. So in that case, you would say, okay, so the speed is 5 times the speed of light? Nothing can go faster than the speed of light, right? Kind of a rule. And so once again, it's easy to see why people would discount that. If you get the speed that you calculate from this as close to the speed of light, you have to shift to using the relativistic. So this was the non-relativistic. For the relativistic, the speed is that. Relativistic means if the speed you get is bigger than about 1/10 the speed of light, then you have to shift to use the relativistic formula. So now if we take that same factor of 5 for z, we'd have 5 plus 1 is 6. So my example here is right, the non-relativistic gives you an impossible result. If we do the relativistic, 5 plus 1 is 6. 6 squared is 36. 36 minus 1 over 36 plus 1, c, equals 35 over 37c. And now we have a speed that's just very, very slightly under the speed of light. That would be 0.946 times the speed of light. So the relativistic equation, you'll never have a calculated speed that's higher than the speed of light But the bigger that Doppler shift, the faster it's going. You can calculate how fast it's moving away. And then you go to Hubble's law, and when you calculate how fast it's moving away, you can calculate how distant it is from Hubble's law. So what did Schmidt get out of all of this? That these things are really far away. Right? The speed was a stepping stone to understand that they're really, really far away. And so once you have that established, I'm looking, the light's off in my office. I was wondering why, since my son's working in there. Once you have established that they're very, very far away, then you have a whole different issue. If it's very, very far away, and you're measuring a fair amount of light, so it looks like a star, what does that tell you about the light that's being produced by this object? It's very, very far away, and you can even see it. What does that tell you about the light? Is it giving off a low luminosity or a high luminosity? High. It has to be a very, very luminous object for us to see if it's really distant. In fact, their calculations now show that some of these quasars have a luminosity that's equivalent to, 10 to the 14th suns. 10 to the 14th would be a million times, well, it would be to 100 times a million suns. It's a lot. It's more bright than any galaxy. And so now you're an astronomer, you're like, I found something that's 100 times brighter than the brightest known galaxy. What in the world? Would you be a little stumped? Okay, good. I see some nodding heads like, yeah, that doesn't make a lot of sense. Well, with the Hubble Space Telescope, we're able to see things that we weren't able to see before. And we can see that these quasars have a, quote, host galaxy. Host galaxy. The pictures and using Doppler measurements of the gas from the galaxy and the light from the quasar show that they both have the same Doppler shift. They're moving away from us at the same speed. Hence, they're together. So these quasars come with galaxies. Is that a question? No. Okay. These quasars come with galaxies. So there's one clue. Okay, so these come with galaxies. It's something in a galaxy, probably. We have jets that are observed from some of these things. Actually, I should go back. There's a jet right there that came out of that quasar. So you have jets that come out of them. And so the question is, what's going on? Now we're going to shift our focus here a little bit to understand it. Black holes. I've told you that we now believe that every galaxy has a black hole at its center. And so this is a picture from M87 where they were able to use Doppler shift measurements to record the speed at which things were going around near the center of this black hole. And so they have, this is going away, this is coming toward us. And you have those Doppler shifts telling you how rapidly the material is rotating. And based on that rotation, they can tell us that between those two objects is a mass of 5 billion solar masses. 5 billion solar masses. There's only one type of object that can have that much mass in that small of an area, a black hole. So scientists are really sure that there's a black hole there at the center. So in studying galaxies, they're pretty sure that every galaxy has a black hole at its center. Now that's a very massive black hole. I cut out some more pictures that were from the textbook of other galaxies with smaller black holes. Here's another interesting, unrelated fact. This is a picture. Okay, this is not an actual photograph, mind you. It's a computer-generated picture of what our galaxy should look like from the side. And these here are illustrating bubbles, as they call them, of X-ray and gamma ray emission. We have some residue out there in the halo that indicates that the solar system at some point must have had some jets shooting out. Now, by this point, you probably figured out the story. The quasars are believed to be the result of the black hole at the center of the galaxy that's having a snap. And yes, that's the words that our textbook uses. When stuff falls into a black hole, it gets accelerated and goes really, really fast. And so there's a huge amount of energy involved. And when that stuff falls in, which does not happen rare or commonly, but when it falls in, that black hole is going to have some material that goes shooting out in jets along the axis of the rotation. And so you have those jets that come out, and when we're looking at a quasar, you're looking at where you have stuff coming out, energy coming out of the poles of a black hole at the center of the galaxy. So these quasars are looking at the black hole of the galaxy where it has stuff. Now, is it coming out of the black hole? No. It's stuff that was being pulled in and then shooting jets out before it gets into the black hole. So here's some pictures to illustrate how the jet forms. Now, this is showing two different geometries for the accretion disk. The accretion disk, you have stuff that's orbiting around the black hole. Because of collisions or rotation, it flattens out kind of into a plane. But some flatten out more than others. If they flatten out really flat, then the jets are going to spray out in more directions. If you have a fat ring, then it's going to be a more focused jet. So when we say, we can't see a black hole, nope, we can't see a black hole. You see it has black here where the actual black hole is because we can't see it, hence the term black hole. But then you have the accretion disk, stuff you can see, like the stuff that they did the Doppler measurements on M87 to determine how much mass there was. And you have the jets shooting out. Do those jets always shoot out? No, only when it's having a snack. So here's an actual photograph of jets coming out of an active galactic nucleus. Getting to the end now. How many quasars are there out there? How many active galactic nuclei are there? It is not just predicted. When we look out in space, the farther away we're looking, the further back in time we're looking. So we can make measurements today of what was going on billions of years ago if we can observe very far things. And so this isn't just conjecture. Should have been soon after the Big Bang from our best measurements. And you see, I believe the one on the left is just calculation. The one on the right is taking actual data points of, at this distance, how many do we find? At this distance, how many do we find? You see they match up pretty closely for you would have had a lot earlier and less as time goes on. Why would you have less and less as time goes on? In the early days of the universe, you would have had more hydrogen, more gas, so you're going to have more stuff that is making star-type things. But as time goes on, you convert that hydrogen into helium and then into iron, and you have less stuff to make stars. So basically the material is thinning out. Furthermore, the space between things is thinning out because of the expansion of the universe. So if you don't have something fall into the black hole, you can't have a quasar. So as you get rid of stuff and as you stretch farther apart, you're going to have less of them. Now that's Obviously, we still have them. Many, many quasars are found when we have galaxies interacting with each other. Our galaxy is currently interacting. It's not beyond the realm of possibility that our galaxy could any day have something fall into its black hole and erupt. And if it did, well, life would be very different for us. Because remember, the radiation coming out there is, more than the entire galaxy just coming from that one place. So it would be super interesting if the jet was aimed right at us. Well, that would be more than super interesting. It would be probably deadly. But it could happen. Nobody can predict. Some other things I didn't say about quasars as I was talking about them. One of the odd things about quasars is that they're very unsteady. The amount of their luminosity varies pretty dramatically under short time frames. Like in a month, you'll have a change of 30% in the luminosity, in the light coming out of a quasar. That can't happen for a big object, like an entire galaxy. Entire galaxies are way too big. Right? If you take the time it takes light to go from one side of our galaxy to the other, it's much, much longer than that. I think the textbook points out that it's like a light week to get to Pluto. Light month is well less than the distance from here to the next star. It's 4.3 light years roughly to the next star. And so if you have a dramatic change in the luminosity in just a month, you have to have an object that's less than a light month in size, which, considering how big we are compared to a galaxy, is a really small object. So that's one of the pieces of information that led scientists to say that even though we have the quasars are associated with galaxies, they have to be a small thing in the galaxy. It's not the entire galaxy is lighting up. Okay, this picture is just looking at data on galaxies. And the textbook says scientists don't have an explanation for this, although, once again, as Alex was the person who used the example of using logic, it makes sense to me. The more massive a galaxy is, the more massive its black hole is. Doesn't that intrinsically make sense? So while we don't have a strong scientific theory why that should be, to me it makes sense. You start with a cloud with more mass. We're going to have more mass that clumps in the center, making a bigger black hole. It just seems logically sound. And that's what has been observed for galaxy sizes. I think this is my last picture. This is an artist rendering of what happens when material falls into a black hole. And so it's just showing something started out there as a red star. Is it a red giant, a red dwarf? I can't say by looking at the picture. I'm going to go with a giant. As it gets closer, what happened to it here? It got stretched. Why did it get stretched? Tidal forces. We just had an exam. That word's on top of your brain now. Yeah. Tidal forces are stretching it, and stuff is being pulled in. And so this stuff will be orbiting around, but when it falls in, that's when you're going to have the eruption. Oh, no, this is the last picture. This is, honest goodness, the last picture. So the last picture here is just to once again remind us that these active galactic nuclei are primarily found, or not primarily, but more commonly found in interacting galaxies rather than in isolated galaxies. And with everything we put together, it's easy to guess why that would be. If you have interacting galaxies, you're much more likely to have material that comes flying through in the vicinity of that central black hole and gets pulled in. Whereas if you have a galaxy that's in isolation, you're not going to have anything disrupting it. Okay, any questions? Mira?
So with this timeline of quasars and with galaxy formation stuff, how do we explain the timeline from a creationist standpoint? Because we have all these billions of years numbers going around.
Okay.
I have a couple ideas, but I don't know.
It's a really good question. Remember, in this class, I talk straight from the scientific understanding. And so sometimes I'm speaking against what I believe in instances, although I try to point it out. I tend to believe in these old ages, that the universe was created by God, by Him setting the laws of physics, and then putting in the energy to create the beginning of our universe, and then at a later time he created life. That's my belief. So this is in complete agreement with my creationist belief. But for a young Earth creationist, somebody who believes that the entire universe was created at the same time that the Earth was created, then this creates a real tough time analyzing. Because after all, when we're looking at this slide, we talked about the Hubble law. And we start off by saying, so we have these things that are millions of light years away. Well, if the entire universe was created 6,000 years ago, we can't see things that are millions of light years away because they weren't there. Well, there is an answer creationists give. They say God created Adam and Eve as mature humans. He didn't create them as infants who had to grow into adults. Right? It's pretty clear. And so why would God choose to make the universe as an infant universe? Why not make the universe a mature, stable universe when he created the universe? And so if he created a mature, stable universe, then he would create it with what should have been there if it had been around for a long time. So that's one explanation that people give, that God created things so that they would look old. Not to trick us, but to make a stable system. If you believe that he created 6,000 years ago everything and did not do that, then you should see stars blinking in all the time. And the distances are moving farther and farther out because time's moving farther and farther out. Yes.
Oh, so those are the two ideas that gotta come up with. I just like to hear, because we keep seeing all these videos. I'm like, just see from a different point of view if you had anything else. Okay.
All right. Have a great day. I'll see you again on Friday.
I don't ever remember any public school class taught astronomy. The closest I had was earth science.
So you have some of that, like, the Earth is about shape and form. Who knows how long it was a ball of rock sitting in the universe just sitting there? It's just like something.